हेलो। कुछ तो सुना ही नहीं दे रहा। गुड आफ्टरनून।
Good afternoon, sir.
या I mean, how many participants are joined from the OAV?
Excuse me, sir. I am from KIT International School. I have no idea.
Okay,
Jharana Pani,
okay, nice.
sir.
Because actually it is a, I mean, pathetic to see because we got the registration more than 50 persons from the OAV, and this is a kind of program we arranged. I mean, from getting collaboration from foreign collaborators from the TIFR, and it is a kind of thing we try to give such some sort of professional attainment to the teachers. I think since the OAB authority circulate, I mean, teachers are already registered, but they are have apathy to the join this program, I think.
Maybe 3:30 is the timing, so I think within 5 minutes they are
Yeah.
trying to join.
Good evening, sir. Good
Yeah.
evening, sir.
Good evening.
Myself, Joshna Vindani. I'm from OAP Patharchapa Balangi, sir. I have joined.
Okay, welcome to these sessions. But we sorry to say that with OAB we got the huge registration from OAB. I don't know why when the teachers they are not interested to join, why they are registering. I mean, since this program, we actually we thought that this time we should inspire the government teachers basically. That's why we are not circulated the notice among the five. I mean, the schools, other schools in the Bhubaneswar, Kotak, or any other in the Odisha. Uh, Apart from getting the more register, I mean, more than 200 registrations from the way we were getting the huge, I mean, very abysmal footfall in the session.
Good afternoon, sir.
Good afternoon.
Sir, myself Divyajyoti Jena from OAV Subarnapalli, Pallahada, Angul district.
Okay, nice. Welcome to this session.
Okay.
And basically, we tried to, I mean, organize this session. I mean, exclusively for you people. And but I think Odisha education sector that there, I mean, it is not a good response. Even after we try to circulate this notice through the secondary education directorate, higher secondary education directorate, OAB authority. Stuart is there. Hello, Stuart.
I'm always there.
Yeah, nice. What's I mean, today is your chemistry.
We will.
Yeah.
So we might give the teachers a couple more minutes just for those which are
Another
trying.
thing I would like to share because last 2 years back, I mean, Government of India formulated new education policy 2020, and that was first time they incorporated the computational thinking in the. They are emphasizing to develop the mindset of the kids in the computational thinking. I mean, my personal opinion is that because it is a new thing that teachers those are educating the students in mathematics, they are not much more aligned with this subject. So you are the best person in the world to teach them in a computational thinking. But it is very pathetic to see the total participations from the government school.
Sir,
So
we are
our-
all from government school, sir.
Yeah.
I am from government school, sir, from Balangir. So lots of government school teachers have joined, sir.
and you're most welcome.
Sir, thank you very much. Thank you very much.
So Suman, we will be doing the computational thinking on Saturday.
Yeah. That's the one thing. Physics is the most of the demonstrators, and chemistry little bit. Most of the cases, time we generally demonstrate, but it is a computational thinking. I think it is a very new, and that's teachers, they should have the such. It is a kind of new thing to them, and it should be adopted by them, because this is a necessarily required for the new generation's student.
We still seem to be getting a few people joining us, so we might give it a couple more minutes before we start.
Yeah. कितना participant हुआ? So I request the participants, tomorrow is the session, is another very good sessions from the TIFR team. And yeah, if you don't have any class or any professional engagement, you should join. I mean, we are fortunate to get all these sessions with the different collaborator without paying any money. We are offering this kind of facility to the teaching community of Odisha. But I mean, it is a very bad field. We feel very bad. That's, I mean, they are apathy to join all these things, because some of the due to COVID, these virtual sessions, we could able to bring some international science communicators, science enthusiastic, science educators to bring in a platform. Otherwise, if it is in a I mean, it could not be possible in a physical form. So try to understand other, even if you are found that these things are very good and helpful to your pedagogy, and try to propagate this information to the other teachers too. So those are not, I mean, they are not within our purview, and they are not able to, we are not able to communicate them. Shall I start the session? Hello. Okay, we should not waste the time. That's, I once again welcome all participants, different teachers from the Odisha, along with the Dr. Stewart. You probably don't know Dr. Stewart is a very famous, internationally acclaimed science communicator. We are fortunate to getting him in such kind of session. And he, I mean, from US to European country, from the Singapore, everywhere you can find, he is always inspiring teaching community with their different kind of activity related to the physics, chemistry, and sometimes computational thinking. So today he's tried to motivate you some sort of, I mean, experiment in chemistry. And what is his motto? His motto is this very, I mean, it's a kind of thing is that he is promote that such kind of activity with the humble materials. That's, you don't need any costly material to making teaching skills or having any kind of, I mean, very precious items to show in the classroom teaching. And I would like to request Dr. Stewart. So this is your, I mean, this is your time, please. Dr. Stewart, hello.
Thanks. Thank
Yeah.
you very much.
This is right now your turn. Okay, thank you.
Thank you. But before we start, just a couple of things. I'd encourage you to keep your microphones on mute when we're doing the activities. But I'm particularly interested to actually interact with you. So I am not a fan of lecturing or just talking at people. As you'll see from the title that we chose, this is not only about doing science and today doing chemistry, but about trying to get students to think. So one of the things which we recognize across the world is that traditional teaching may be good at transferring some facts or content knowledge from a teacher to the students. If it's done well, the students can get the content knowledge. But the school system and the country and the communities are all looking for students that have additional skills, that they have skills of critical thinking and problem solving and deep understanding, not just a surface memory of the techniques to solve a standard problem. And certainly one of the things which I'm always asked about when I visit India is to comment on the large number of Indian engineering graduates that the engineering industries of India, it's not me, but the industries that employ engineers in India have been reported as saying that maybe 70%, 70% of the graduates, the engineering graduates, are not ready to work. They're not work ready. And a lot of that comes from the students are very smart. The schools have worked very well, but they have been taught a very narrow set of content, and that they might not have had the chance to practice critical thinking, to actually think deeply. It's probably more complex than that, but I think that's one of the challenges. Last week, I was in Singapore working with one of the science centers there, and Singapore faced the same challenge 15 years ago, that they were training very, very bright students, that if you gave them the problem to solve, they would solve it very quickly. But if you didn't shape the problem or describe what kind of problem it was, they struggled. And so one of the things which I spend most of my time finding ways to support is getting students to think more deeply. And for us as educators, often means for some of our teaching, we should turn it round and we should do it what might feel backwards. So often in our teaching, we might give them the theory, we might do a demonstration that demonstrates or proves the theory we just gave the students. It's very valuable to sometimes do that in reverse, to actually give the students an experience, a chance to try something, a chance to see something, without the teacher telling them what it's about, without the teacher giving them the answers, and asking the students to think about what they saw, to get the students to try and make sense of it, even if the students don't yet have the content knowledge, the facts about it. And what that little reversal does is it gets the students curious. It gives them a little chance, a small chance, to try and solve a problem themselves. And then when the teacher brings the additional information, facilitates the students, then that knowledge that the teacher is sharing can fit in and, if you like, help the student resolve the problem. And so the knowledge is seen as being useful because it answers a question that the students already have. So during the next hour and a half, 2 hours, I'll be showing you some activities that relate to different aspects of chemistry. I expect, because many of you will be very experienced teachers, that you will probably have done some of these activities yourselves or done similar ones. But I will try to bring in some new activities, some activities that you might not have tried, but I'll also be getting you to think about what we're seeing and to see how you would go about answering it, and think about how your students might go about answering it as well. So let's make a start. During the session tonight, I would greatly appreciate it if you've got a question, or if I'm asking a question, pop your thoughts, your answers into the chat window, and I will check on that to see how we're going. This is not an exam, so we're not going to be marking you on whether or not your suggestions are right or wrong. So we should feel comfortable sharing our first thoughts, just as if we were the students. So let's begin. So one of the topics which is taught in chemistry everywhere across the world is the topic of acids and bases and pH. And some of that content is fairly digestible. The students can understand some of that. Some of the concepts in there are a little challenging. The pH scale and the logarithmics of that, and doing some of the calculations. But let's look at how I bring some of the acid and base topics in. And as my good friend said at the beginning, just about everything I'll use tonight I use the word humble. Should be quite available to you, even to your students when they go home, which is another reason I use the simplest materials I can, so that if the students want to try it again, they can do that at home. So acid and base, as I said, is a very important concept that we teach. Of all the countries in the world, one of the countries that should be most familiar with this material must surely be India. If anyone in the world is familiar with turmeric, it must surely be the cooks and the hungry mouths of India. I hope that many of you know that turmeric can be used to create an acid-base indicator. So hopefully you're aware of that, and that's one of the materials that you use. Just in case some of you haven't used that or seen how it's prepared, for me, my standard way of preparing indicators using turmeric is, here in Australia, very hard to get fresh turmeric. It's very expensive, but we can get dried powdered turmeric. And so I would take a few large spoonfuls of this into a bottle. And if I've got some alcohol, so methylated spirits, alcohol, I would add about half of the bottle. So I would add about half of the bottle full of alcohol. And I'm sorry, can we just have people muting their microphones for the moment? Otherwise we're getting some bad echo. Thanks very much. And so I would just put the ground turmeric into the bottle with the alcohol and shake it up. And I might add an equal amount of water after I've shaken it up for a while. And what you get then is a wonderful extract of the pigment that makes the turmeric yellow. We know what the chemical is. It's curcumin. And this is what will stain everything if you spill it on there. But we'll now move over to my workbench. So I'll change cameras. And we'll just show you what turmeric is able to do as a pH indicator. So here, just for tonight, I'm just using an ice tray. And I'll just put a little bit of water into a few of the wells of that. You can see I'm being very scientific, very careful with all of the amounts. And what we can do now is I'll just put a few drops of my turmeric extract. You really don't need very much into here. And we can see its kind of normal color, or its color as I've extracted it, is that kind of wonderful bright yellow. And that's the color of turmeric as it will probably be for you when we extract it. So what I've got here now is some vinegar, some acetic acid, and I'll put a few drops in the first well, and nothing much seems to happen. It's perhaps gone, if you can see it on your camera, I think perhaps it's showing up. Perhaps it's gone a lighter, brighter yellow, kind of less orange. And that's the color under acidic conditions. Now, I'm assuming everyone here is reasonably familiar with chemistry, that you're all science teachers and probably chemistry teachers. Into the next well, I'm going to put some sodium bicarbonate. So this is a solution of sodium bicarbonate. And we can see it's gone to, you might call it either a deep brown or a dark red color. And sodium bicarbonate, we understand, is a mild base, a mild alkaline. And here in this third cell, I'll go and put a few drops of cloudy ammonia, which hopefully that's showing up on the camera. The colors change a little bit on the cameras, but that's gone to an even darker color. So we can see from this, we can use turmeric to identify and tell the difference between acids, moderate bases, and strong bases, strong alkalis. And one of the ways I often use this, or I encourage teachers to use it when they're working with their classes, is if you've extracted the turmeric with alcohol. So here in Australia, methylated spirits is relatively cheap. So I'll extract that, and then to prepare for the class, I will just go and get just some normal cheap printing paper, so printer paper, and just a small brush and the turmeric. I will just quickly paint the paper with the turmeric extract. The alcohol will evaporate off in just a few minutes, even on a mild day, but somewhere warm in the direct sunlight. And you will then end up with turmeric paper, which is what I have here. And so even a couple of teaspoons of turmeric will make a dozen pages of this sort of turmeric paper. And we can use the turmeric paper, cut it up, use it like we would litmus paper or pH paper. And this is something which can be easily given to the students. They don't end up spreading turmeric dye over everything. And we can see if I put a little bit of the ammonium hydroxide onto the yellow paper, just get a drop or two, we can see there just how dark that's going. If I put that back into vinegar, we could neutralize it and the color would come back. And so we can use these as test strips. And once it's made like this, if you put it somewhere cool and dark, so just into the pages of a book, put it on the shelf, stop the sunlight from bleaching it, this will last easily a year in storage. So you don't have to make it on the day, you can make it quite some time beforehand. So that's kind of making one of the tools, and I'm sure you're more than familiar with how you might set up activities for the students to use a pH test like this. Checking the the strength of vinegar. Has vinegar been adulterated? Have they watered the vinegar down? You'd be able to spot those sorts of differences with a test strip made from this sort of turmeric paper. So hopefully that's reasonably clear how you would put it together. As I said, I expect many of you will probably have already used that material.
तुमको जाना है तुम क्या इसके लिए आए थे? मैंने बोला तो सेल्स का जाएगा नहीं.
So we've got one of the questions there. Which chemicals do we add to the turmeric? I just add. Let me just change cameras. So you can use just hot water to extract the turmeric. You will still get the color to come out. You won't get as much color to come out in the water as if you use an alcohol solution to extract the color. And if you're making the paper, if you paint it with kind of wet turmeric or turmeric extract with water, it will still dry. It will just take longer. So if you've got 50% alcohol, 70% ethanol, that will be fine. It's not very fussy. All right, very, very forgiving. So even hot water, you'll get an extract which you can use. But if you want to make intensely colored test paper, it's better if you extract the turmeric with some alcohol. It'll just work better. You'll get a more intense dye into the paper. So there's a question there. Other than turmeric, what can you use? At the end of the workshop tonight, I will share my email address. I've got some pages of alternative natural pH indicators that you can find, and we'll see one in a moment. So there is a lot of alternatives to turmeric. Turmeric is very good. It's very available, particularly in India. It's very cheap, but it does tend to turn dark red at very not sure who keeps muting me. But turmeric turns to a dark red at a very high pH. So 7 or 8, it'll still be yellow. Not bright yellow, but it'll still be yellow. It's only when it gets to kind of 9, 10, 11 will the turmeric start to go very dark. So it's not good if you're looking at neutral to mild alkaline solutions. One material, so Harpreet has kind of mentioned red cabbage. All right, so I was going to check with you as to which kind of colored vegetables and colored flowers are available in your part of India. The fact that Harpreet's mentioned red cabbage means that they've at least seen it there. So red cabbage is a fantastic source of pH indicator. Again, rather like the turmeric, but you don't need to use alcohol to extract the color. So I would take a red cabbage, cut it up quite finely, put to a small cabbage, I'd put a liter of water with it, and I would cook it, steam it, boil it slowly on the stove for about 20 minutes. Doesn't need to be much longer than that. Strain it off and keep the liquid, and you can eat the cabbage afterwards. I always eat my cabbage after I've extracted the pink dye from it. It's a little heavily cooked, but it's still perfectly good to eat. But most red flowers, most blue flowers, and most brightly colored vegetables, particularly if they're purple, will work. You can extract the color. It will almost always be a pH indicator. This I made this afternoon from that red cabbage that you saw, and we'll have a look at this over on the workbench. When I'm not using this, I will put it into some small bottles and I will put it in the freezer, or you can leave it in the fridge, somewhere dark, and freeze it. This will last for a year. This will last for a year, particularly if it's frozen. Just take it out when you want to use it. So this has the advantage over turmeric in that we get color changes across more of the pH range. So you can use the two together if you want. What we'll do is I'll set the red cabbage up over on the workbench, and we can have a look at what the colors are that we get there. So let me just quickly do my washing up with this, and I'll show you tonight what I think is a particularly valuable activity that we'll do with the red cabbage dye, the red cabbage pH indicator. So I'll just use these wells at this end. The turmeric, as you can see, and anyone who is a cook knows just how good turmeric is at staining things. So I've just put some water into those 4 wells, and hopefully you can see the nice purple color that comes from the red cabbage. I think they should call it purple cabbage, but they call it red. And you can get something similar from beetroots and purple carrots, if you've got dark purple carrots. So this again is the color as it's been extracted from the cabbage. I haven't done anything except boil the cabbage slowly with a little bit of water so the color is concentrated, poured it off carefully, leaving the cabbage behind. I haven't even filtered it. So this is the color that it is after I've treated it that way. I'll put some vinegar in here, and hopefully you can see on the camera, yep, the colors aren't accurate, but you can see the color difference. So the extracted red cabbage is this kind of purple color. In vinegar, it goes to a light magenta. If I put in some of the sodium bicarbonate, put a few drops in, this is concentrated bicarbonate, sodium bicarbonate, the purple moves to sort of depending on the concentration, to a deep green or a blue. And I'll put some of the ammonia in here, and that's gone to a very dark, well, almost a bright green. So we can see we've got some strong color changes across a nice wide range. So around neutral, it's purple, acidic, magenta or pink, red. That's where the red cabbage gets its name from, because the cabbage is often pickled with vinegar, so it goes to this color. With a little bit of bicarbonate, so mild alkaline, it's a blue, and strongly alkaline, it's dark green. And so that's a very useful pH range to work with. Particularly good if you're doing kind of wet chemistry rather than the test paper with that. So that's sort of putting together the tools to help you and the students do some of their chemistry. But let's kind of look at one of the activities that I would actually set up and use this for, which is where we start to get into some kind of interesting science, not just the techniques of setting that up. And so for this next activity, I'll just change cameras as well. Hopefully that's going to focus. It looks as if it has focused a bit. Sorry, everyone, I'll just check and see that that is focusing. It was focused before. All right, that's reasonable there. So for this activity, I've just got a small glass jar. Doesn't really matter. I don't use real scientific equipment. Whatever is to hand, and I'm just going to add to that just some tap water, which in Canberra is pretty good and is normally neutral, normally pretty neutral. And I'll just add some of the red cabbage indicator to it till we get a reasonably dark color, something that works on the camera. I think that's okay. And what I'm going to do before I start this little experiment is I'm just going to make this solution very slightly alkaline. So I'm just going to put in 1 drop of, this is just household cloudy ammonia. May have put in more than a drop there, but that now is almost an emerald green, a bluey emerald green. So I've made the liquid in there slightly alkaline. And what I'm going to do now is I'm just going to get a piece of tubing. You can just use a straw if you've got access to that and COVID allows. And I'm just going to start blowing, exhaling, blowing bubbles in the liquid. All right. So I'm just going to start blowing bubbles in the liquid. And before I start, because we are scientists here, so I'm going to do a control, put a little bit of the liquid over here in the other bottle, so we can compare the colors later after I've blown through this one. So here we go. Already, perhaps you can see it on the screen, perhaps not. It's already moved from the kind of the emerald green to a teal blue. It's now back to that purple violet. And if I keep blowing, it may go even further. Probably can't get it to move all the way over to sort of, cherry red, but I think you can see just how much the color has changed. And so, as I was suggesting to you earlier, if I was working with the students, I might very much, once we've looked at acids and bases in general, and they've had a look at the colors that we're showing them and the way that the indicator changes, I might get them to do that activity without telling them really what is going on. I would just tell them how to set it up, start blowing, see what's going on, and to then ask them to think about what they saw and what they think might have happened. And just get them to come back and go, you saw the color change, you've seen the other color changes with the acids, the bases, and the alkalis that we've done as a test. What is this telling you about the activity they just did? And they might have all sorts of different answers. And when I'm working with the students at that point, all ideas are good. All ideas are good to hear, because that tells me as an educator what's in the mind of the students. If I gave the students a handout with all of the printed instructions to follow, I can't really tell what they're thinking. In fact, they probably aren't thinking very much. They're following the instructions. So it's not really an exploration of science. It's really an exploration of literacy. Can they follow the instructions? And what I want to do, even for just a few minutes, is to go, you saw what happened. Think about it, because you can make some deductions. Even though I might not have told them, they might not know about our breath is rich in CO2. They might know that, they might not, but they will have seen the color change and they should be able to begin to make some sense of that. And then I would work with the different answers of the different students to try and see whether or not there was a consensus, whether or not they were sharing their ideas, whether they were critiquing each other's ideas, because this is all part of critical thinking and problem solving. And that doesn't have to take very long. It could be 5 minutes, could be 5 minutes. And then as an educator, I might step in and help them clarify if they hadn't worked it out. But I would give them the chance to explore the ideas first. Again, doesn't have to take very long. They're more ready to listen to your explanations once they've tried to answer them themselves, or at least most students are. So for the teachers here tonight, can you explain what happened and what we saw? I think we know what we saw. We saw the alkaline green indicator change to the purple, which we saw from before kind of means it's more neutral, heading back towards the acidic end. So why did it change? Why might it have changed? What are your thoughts? So we've had one suggestion that we sort of blew the carbon, we blew bubbles through it. Our breath has carbon dioxide. And I'm starting to get some chemical answers now. We made carbonic acid. So yes, that's, so we had CO2. We think that it's a CO2 in my breath. That's making carbonic acid, and that's changing the pH of what's in the container. And that's probably true. That's probably exactly what happened. But if I was playing with you, I could say that sounds like a good explanation, that it's the CO2 in my breath. But how could I confirm that? How could I test it? Because maybe just blowing bubbles through there took the ammonia out. So maybe it wasn't me adding something to it. Maybe it was just me blowing the ammonia out of solution that shifted the pH back. So that's another hypothesis. That's another idea. How can we test? How can we work out which of those possibilities was true? Because that, coming up with a way to test something, That's science. All right. All of this other stuff is knowledge. Science is when we have an idea and we can think of a way to test it. So you know a lot of science already and you're applying it to what we saw. And it is the CO2. But tonight we haven't proven that it wasn't me just blowing the ammonia out. So we've got two possible answers, and we haven't tested either of them really. So we could, okay, Sushil is going. We could do the test of lime water. So I've got some lime water here. We won't do the test. I think you all know it. So we could put some lime water in a vessel. I could blow through it and it'll show that there's CO2. So that confirms that there's CO2 in my breath, but that still doesn't confirm that it's the CO2 in my breath that's making this bottle change. Because the CO2 might be there, but it might still mostly be the bubbles taking the ammonia out. How could we resolve these two possibilities? I might leave you to think through that, but this is the kind of challenging that, depending on the age of the students and the subject, I might not give them an answer today. I might go, probably this, maybe that, but the evidence doesn't rule out this other idea. How do we rule out the other possibilities? And that's critical thinking, and that's real science when we start to think about how we disprove ideas. Once I've done, so it is the CO2, but if I was being hard about it, we haven't discounted the other idea, not really. But we can see from this, if we accept it, and I do, that CO2 going into the liquid is making it acidic. Is that a problem anywhere? Is that a problem anywhere else? CO2 going into liquid, making it acidic? Is that a problem anywhere? Can anyone think of a place where that happens, or a place where that's a problem? Any thoughts? Any thoughts? Pollution in water? So what sort of pollution in water? What sort of pollution in water? I think if I'm going to pronounce that name, Bayeta, I may be making a horrible mess of that pronunciation. So what sort of pollution in water are we thinking of when we say that? I was thinking of a couple of places where this happens and it's a problem. One of those is kind of in carbonated drinks. So these have got a lot of CO2. That's where the bubbles come from. That's what the bubbles are. And we could have used this to pour in there to see if the pH changed. So CO2 combining with hemoglobin, reducing oxygen. So great idea, great instance of where CO2 is at play. And CO2 does acidify the blood a little bit, and that changes hemoglobin. So CO2 in drinks makes them acidic. So does a lot of other things they put in there. And that can attack your teeth. It can weaken your teeth. I'm sort of coming back to Bayeta's suggestion. There's a really big problem. There's a really big problem with CO2 and water. And that's in our oceans. So as mankind continues to sort of burn fossil fuels and release CO2 into the atmosphere, not only is that becoming a greenhouse gas in the atmosphere, but the CO2 is dissolving in the oceans, just as my breath was dissolving in that bottle. and it's making the water in the oceans more acidic. And we can actually see why that's a problem again, or just set up a very quick, simple demonstration of that. I'll take that bottle. I'm going to fill this container up with vinegar. So that's pure vinegar, which is more acidic than the ocean. Even at the moment, it's more acidic than the ocean. And I'm hoping that my chickens have laid eggs that are too big. That's typical. I look after my chickens far too well, I think, if that's the case. So we'll change container into this one. Just need a bit more vinegar. So many of the organisms in the oceans have shells. They have bones, they have shells on their outside, and these are essential for them living. And here is a chicken's egg, and a chicken's egg is made up of the same minerals that many of the shells of our marine creatures are made up of. And in no time at all, hopefully you can see bubbles forming on that and rising up. We're dissolving the shell off that egg. And in a day or two, all of the hard shell will be gone. And that's one of the challenges which is facing our marine life. So even fish, you might not think they have, a lot of calcium in their bones, but they do. And the fish feed on plankton and diatoms, and all of those creatures rely on calcium to go and make shells. At least the zooplankton require that. And the more acidic the ocean is, even if it doesn't kill them directly, it means they've got to spend a lot more energy to try and capture the calcium to build their bodies. So it makes them less efficient. So it's not directly responsible for the coral bleaching, but it stresses the corals and it does dissolve the calcium out of the corals. So it makes them more stressed. So when we get heat events, hot water events, heating events in the oceans, they do bleach more easily because of the acid, but it's because of the stress that has put them on. And so here we've sort of gone from some puzzles about some acid and base and CO2 and respiration, and now we've been able to link that all the way through to issues of global climate and challenges at that scale. So hopefully that pathway, that connection there is something which you might like to think about if you haven't made those connections within your teaching. Are there any, let's come back to this. Are there any particular questions about the activities that we've covered at the moment? Because we're going to sort of take a step into kind of a different topic in a moment. If you've got any questions about either what we did or what we covered, or some versions of that you do yourself that you'd like to share with the teachers, we could do that now. Otherwise, we'll kind of step over into a different topic. I'll give you 37 seconds to think about that, whilst I just warm up some water and clear away my egg. Any questions? No, we're all good. Okay, all right. So we've done some acid and base. Have the students collect flowers, bring in colored vegetables, see what they can do. That can be a project just in itself. And then you can get the students to help make the pH indicators, which they can use in their own projects or the projects that you set for them. So if they're making their own pH indicators, they can go home, they can check things in their kitchen. Are lemons acidic? They can do all of that inquiry, that investigation at home with pH indicators that they've made themselves. And it's just cabbage juice and kitchen ingredients. So we know it's, safe. These aren't dangerous chemicals. They put these in their mouth all the time. Okay, Harpreet's shared that they sometimes use this to go and write secret messages. So there's a lot of those different applications depending on the age of the students and what kind of curriculum subject you might be they might be moving through. What we're going to look at now, if the materials are kind of ready here, is the subject of diffusion, which I love the topic because it's not only important in chemistry when we think about chemistry, but it's even more important when we think about biology. So I tend to like those sciences or those bits of science which become sort of important across a number of different areas of our teaching. Because a student might be interested in chemistry but not biology. They might the reverse. They might be interested in biology but not chemistry. These are all ways to help them find an interest. So I'm just putting some room temperature water in there at the moment. And I'm just going to top that up with some recently boiled water. This isn't Pyrex, these are just vases which I've taken the flowers out of. I didn't want to put too much boiling hot water in there for fear they would crack. All right, so that's some quite warm water. And in the column next to it, I'm going to put some water that have been cooling in the refrigerator. That's been in the freezer. It's almost got a few small bits of ice in there. It's very cold. We're just going to let those stand there for a moment. So if there's any liquid that's flowing around, swirling around because I poured the water in, that it has a chance to slow down and settle out. So one of these is very hot, one of these is very cold. Same shape, same water, it's just pure water. Like just to get that ice out, so there aren't any additional variables. So one of the things which I like to sort of share with teachers is there's a number of explanations about phenomena that we teach about, some of which is in textbooks, some of which we've been told by our professors, and a lot of which, if you go online to look at YouTube, you will find some consistent explanations. And this is even amongst some of my science communication friends. Unfortunately, some of the time those explanations are just wrong. And this is one of them, all right? This demonstration is one that you may have done. You may almost certainly have seen it, but the way it's normally explained is almost always wrong. So we're talking about diffusion, hot water, cold water. And I'm just going to put a couple of drops of food dye into each of these, and we'll see what happens. 2 drops, 2 drops. And now we'll just see what happens. Can we see a difference already? I think we can. And one of the things that we're taught, one of the things that we're told, is that diffusion happens a lot faster with higher temperatures. So the warmer a system is, the faster diffusion will happen. And that's true. That's absolutely true. That's not wrong. And this is hot, and this is cold, and this is mixing very, very quickly, and this is not. But this is often shown as a demonstration of diffusion, and a way of proving, demonstrating, visualizing that diffusion happens faster at higher temperatures. That's the bit that's wrong. These are mixing faster at higher temperature. This is mixing very slowly at cold temperatures, but it's not because of diffusion. There's another process happening here, which is the main process. Can anyone tell me what that is? What's the real process that's happening here? Can anyone tell me? So dissolution is not the word I would be looking for. Keep thinking, what process do we actually see happen? So Betta's mentioning kinetic energy between the particles of the hot water. That's true, but that's more the sort of explanation that you might find that talks about diffusion, which is the kinetic movement, or all movement is kinetic, or the movement of the particles, movement of, in this case, the molecules. And the higher the temperature, the faster the molecules or the atoms go, and so diffusion happens faster. That's absolutely true. That's absolutely true. I'm going to set up another demonstration here. This is just kind of room temperature water. And I'll just let that settle down. And while I'm doing that, I'm going to ask, is there, so we've had one bit of information shared with us, which is correct, that says the higher the temperature, the faster diffusion goes. Is there anything else that drives diffusion, as we often talk about it? What I'm thinking about when I'm asking that question is, we'll often say that you have diffusion sort of along or down a concentration gradient. Right. That's what we'll also we'll explain that to our students, and that's true. A lot of these things are true. All right, just about got this other activity set up here in just a moment. And that first activity there I showed you, which I'm saying is not diffusion, is very, very common, very commonly done, very commonly included in textbooks as well. So what I've got here is just room temperature water, and I've just put some, in this syringe, some salt water, some not quite saturated, but very strongly salty water, concentrated sodium chloride, and some blue food coloring so we can see where it's at. And I've got a little tap here so I can turn it on and off. I'm just going to try and be very careful. I just want to introduce the salt water, which I think we would all know is dense, but it's also concentrated. I'm just opening up the tap, and I don't want any mixing. Just letting that drain in as slowly as I can. Over here, this is kind of almost completely uniformly mixed. It was for a long time. Here, still has not mixed all the way through. Didn't want any bubbles. We're draining the salt solution into here. I'll turn the tap off. And now just going to carefully try and draw that up without letting too much blue drain out. There we go. All right. So now we have a very concentrated salt solution at the bottom and pure water above it. So we should feel confident that that should diffuse fairly quickly because it's a very strong concentration gradient. So what I'm going to do is to try and put this over here without disturbing it. And we're going to come back later and see what's happened. See what diffusion, pure diffusion looks like. The answer to my question here about what was driving that, surface area affects the rate of diffusion. That's a great comment, and we're going to do an activity about that. So thermal energy causes the dye to move faster in the hot water. So Dr. Prashanti has said the thermal energy causes the dye to move faster. That's true. Why? What's the mechanism behind that? What's the mechanism behind that? What's actually happening here, 98%, I'm making that number up, but it's around 98% of what you saw here was not diffusion, it's convection. It's convection, it's not diffusion. So diffusion is that movement of molecules because they've got kinetic energy. Because the molecule's got kinetic energy, it will move randomly in all directions. And that means that it will diffuse randomly. And if you've got a concentrated area, more of those will end up moving into the low concentrated area than will move from the low concentrated area into the highly concentrated area, because it's random and there are more of them in the concentrated area. So more of them will end up moving to the low concentration. Here, this was being driven by convection. This is hot water. It's in a cool room. The water is cooling. As it cools, it gets denser and it sinks. And as it sinks, it draws warm water back towards the surface, to the cooling areas where it cools and gets denser and goes back down. And you saw that. We had this kind of mixing, this tumbling in this, even though I'd poured the water and let it settle down. So this was being driven by convection. So almost all of what we saw there was just convection. This was cool. We had a little bit of convection in the opposite direction. Heat going in, warming it up, but the heat difference was much less. This is about 5 degrees. The room's about 15. This was nearly 100 degrees. So there's a lot of convection happening here. The fact that it matches the story about diffusion is one of the reasons why it keeps being shown as an example of diffusion. But I can assure you that what we saw was almost entirely convection, not diffusion. If anyone's got any questions about that, happy to talk through that. It's important that we have the right ideas. Here's our saturated salt solution in the bottom, and it doesn't seem to be mixing at all. The water at the bottom is the same temperature as the water above. It is denser, but it's also very concentrated. And so if it's diffusion, we should be seeing that spread out. And we are, but diffusion is a very slow process when you think of a big scale. All right, so maybe there's a millimeter on the top of that, where it's kind of going from dark blue to less blue to clear. Diffusion happens very slowly, particularly in a liquid, even slower in a solid. You can diffuse in a solid, but it's very, very slow. Let's one of the participants sent me a message talking about surface area and diffusion. So I have what I think is a really nice demonstration that bridges between chemistry and physics and biology, and it's about surface areas and diffusion. I'll just move that out of the way. We'll come back and look at that a little later. What I made earlier today, was a special jelly. So this I've made today. The color, oh, I'm in the wrong, sorry. I've got the wrong camera up. There we go. So here, is this thing not going to focus? There we go, we're focused. So this is just a tray of jelly, the sort of jelly you might serve as a dessert. This is made from animal gelatin, but you can use agar or sort of vegetarian gelatin, which sort of comes from seaweeds. And the yellow color in there is our old friend turmeric. So I took some turmeric extract, some hot water, some gelatin crystals, mixed in a little bit of turmeric, and then let it set. So now I've got jelly, yellow jelly, but we know that if we put some, say, cloudy ammonia around the gelatin, then where the ammonia finds the turmeric, it'll turn red. So this gives us a way to see how quickly ammonia can diffuse into the jelly, because we will see the color change. So the turmeric's a very large molecule. It's not going to diffuse very quickly. But the ammonia is actually very mobile, so it'll diffuse. And so picking up on that comment that we had earlier, might have been, I'll come back and we'll talk about diffusion. Keep thinking about it and keep putting your approach to how you would talk about what we saw in those blue tanks. So I won't let you go away this evening with the wrong idea. I don't want to be doing that. That would not be a kindness. All right, so I've got the jelly and I've kind of cut it into cubes. And let me just see how cleanly I can get my jelly cubes out. Again, at this point, there'd be absolutely nothing wrong with eating that. Well, there'd be no health problem. It's just jelly and turmeric. So again, these kind of humble materials, not only cheap to do, and the students can try them at home, but it also means that they're almost always very safe to try. So what I'm going to set up now, I'm going to try and get a really nice regular cube of jelly. And if I was doing this in the class, I would probably get the students to measure it with a ruler. But I think that's pretty close to 2 centimeters on an edge. Maybe it's a little short, but you'll have to forgive me. I'm going to say that's about 2 centimeters on a side. Now with the other cube I cut out, I'm going to make a cube which is 1 centimeter on a side. I think it was Sony, if that's the appropriate way to call you. Sony kind of mentioned that surface area and diffusion, there is a connection between these, and there certainly is. So I'm going to go again and make a cube. So each time I'm kind of halving the linear dimensions of the cube. I could go even smaller, but you won't see it. But the students in a class would, so they can go as small as they like. All right, so there we've got, I'll see if I can get the camera in a little closer. It'd be good if you saw it. All right, there we go. So one of those cubes is 2 by 2 by 2. So I'm always in awe of the strength of Indians in doing mental arithmetic. So 2 by 2 by 2 is going to be 8 cubic centimeters. The next one, 1 by 1 by 1, even I can do that. That's 1 cubic centimeter. And the next one down, which is about 5 millimeters by 5 millimeters, so about a half by a half by a half, is about 1/8 of a cubic millimeter, or 0.125 of a cubic millimeter. So now I will find my cloudy ammonia, and I'm just going to pour the cloudy ammonia in, and going to make sure that we cover these. And just so we can have a look at something, I'm going to put an irregular shaped one in there as well. Now, I'm sorry if that camera is not focusing quite as sharply. Very frustrating, I'm sorry. But this, come on, focus, focus. You might see these seem to be changing color, but what is really happening, and I'll take the irregular shaped cube out in just a moment. What's really happening here is the ammonia is diffusing in. And so that red color, that change that we get, is happening from the outside going in on all the faces that are in contact with the ammonia. And so I'll just lift this kind of irregular shaped one out. I'll put the big tank aside for the moment. If you're doing this in the class, you would obviously cover that, otherwise you get the smell of ammonia going kind of everywhere. And if I cut through the piece, I don't know if my camera is going to do a good job of this. Let me just see. If it doesn't, I will find another camera that'll do that. There is kind of a red skin around that that's coming in from all of the sides. And what you can get the students to do is then sort of wait a minute or 5 minutes and then go and measure, because you can see it in here, how far in the ammonia has diffused. All right, so we can actually measure it. So we can do mathematics with this, include mathematics into the chemistry that we're doing. I'll just let that go for a little while, and we'll come back to it. I'm just going to cover that for the moment. Just keep a bit of the ammonia in there and not going through the rest of the space in here, filling up my lungs. So what we have happening over there in the jelly is we're having diffusion coming in, as I've said. We can see where it's up to. And one of the comments from one of the teachers sort of said, oh, the rate of diffusion depends on the surface area. What we'll actually, and that's sort of true, depends exactly what you mean by that statement. If you look at the cube there, which is 2 by 2 by 2, so it's got a volume of 8. So it has a volume of 8. So the volume is 8. What's the surface area of that 2 by 2 cube? It's going to be 2 by 2, so 4 on each face, 6 faces, 6, 4, 24. So the surface area is 24. So volume is 8, surface area is 24. The ratio of those, if I go the ratio of surface area to volume, that's going to be 3 to 1. What about the next cube down, the one which is 1 by 1 by 1? That's got a volume of 1, and its surface area is 1 times 6 is 6. So it has a ratio of its surface area to its volume of 6 to 1. So the smallest cube we have there, which is a half by a half by a half, has a total surface area of half by half is a quarter, 6 quarters, 1.5. 1.5 is its surface area, sorry, on there. Its volume is an eighth, 0.125, and its surface area, half by half is a quarter by 6, 1.5. Which is quickly someone who's very good at fractional ratios. It's about 12 to 1. So they're all the same shape. They're all the same shape. But if we look at the ratio of the surface area to the volume, we see each time we kind of halve the size, the ratio of the surface area to the volume doubles. So if I went again and made a cube half the size again, so about 2 millimeters by 2 millimeters, you would have a surface area to volume ratio of 24:1, right? 8 times what the surface area is here. And that becomes important because the linear rate of the diffusion is the same for everything, or same for all of those cubes. So in a minute, it'll go in 1 millimeter. And in 2 minutes, it might go in 1.5 millimeters. And that's happening on all of the sides, on all of the faces. The ammonia doesn't know how big the cube is. It's just going in through the face. The surface, or the boundary, is where diffusion happens. So we can look at the mathematics, and we can look at the cubes, and we can easily see that the ammonia is going to reach the middle, the center of that small cube much, much sooner than it will ever get to the middle of the big cube. All right. Let's just see where we're up to. All right. It's a little hard to tell with my camera. With my eyes, I've got no problem seeing it at all. So in the time I've been talking, I'll just swing back to the other camera. Perhaps you can see it there. Hope I'm not fooling myself. Perhaps you can with that. That ammonia is diffused in, I would say, about 2.5 millimeters. So on the small cube in there, it's reached the middle. On this big cube, we could do the maths. It's still 90% of that the ammonia has not reached yet. And this is the maths and the diffusion that is behind a lot of the things which we share and talk with our students about when we're dealing with rates of reactions. So rates of reactions are often compounds, reactants, mixing and meeting each other. And if you've got solids in the mix, then the surface area is where the reaction is happening. And so finally dividing something will allow that diffusion, will allow that interaction. And so dicing something in half will double the surface area if we're cutting it into cubes, the surface area ratio. Which is why if you grind things into a powder, the surface area ratio has gone up possibly 10,000 times. Easy to get that increase. And that really drives the difference between reactions. So one of the things which I would do in a class to highlight that difference, if you've got a gas burner or a Bunsen burner, here is just a nail, so it's iron, probably not even steel, it's iron. And if I take a blowtorch to the nail, I have the tip of the nail glowing red hot. Doesn't appear to be burning, but it was red hot, all right? Wasn't burning. It's iron. I'll put this somewhere that won't burst into flames or burn something else. But if I take a little bit of steel wool, and for this, I'll actually probably put it into a little crucible. We'll just have a look at that over under the other bench, so I'm not holding it. Put that away for the moment. And just so we can see literally what's happening. And I'm just blowing on that gently. You can set fire to that steel wool with a candle. You don't need a blowtorch. And that's how important surface areas are. That's how important surface areas are. Because with that nail, that's the same chemical reaction. Iron, heat, oxygen. The nail isn't going to burst into flames. Not by itself. The steel wool will. And it'll heat up faster because of that surface area, because heat diffuses as well. But it's also the rate at which the oxygen can get to the steel. And so the oxygen can get to the steel probably 100 times faster. And so the oxidation that's happening is happening 100 times faster. And so the energy that's released from the oxidation is happening at 100 times the rate, which is able to keep the steel hot enough to keep it burning. And so we've had someone talking about the rate of reactions proportional to the surface areas. So yes, if you're mixing, a solid with a liquid or solid with a gas, it is. So the reaction happens at the surface. So the greater the surface area, the more reaction. And so it's kind of a central, it's kind of a foundational concept. And when we're thinking about, as we were talking about before, about other aspects of chemistry, that surface area to volume ratio is important for animals when we're thinking about digestion and absorption of nutrients, when we're thinking about respiration, when we're thinking about photosynthesis, when we're thinking about an animal keeping warm or getting cool, holding onto its heat or shedding heat. That a larger animal has a smaller surface area, so it will lose heat more slowly. It'll gain heat more slowly if it was cold-blooded. And so this sort of principle that we were using the jelly cubes to explore. We were doing the maths, we were doing the chemistry, but it relates to physics, it relates to biology, it relates to so many important events in our lives that are to do with science and technology, and energy movement. All of those things are important. Do we have any other questions? Do we have any questions about what we've covered there? I will come back certainly before we finish, and we'll have a look at what those ideas of diffusion are that we have and how we would talk about them. All right, I have so many activities we could go into tonight. Sometimes I go very quickly through an activity, but I think tonight I feel that you're kind of engaging with the content and kind of how that might be delivered. So I don't want to just rush through it too fast. Let's go back. We'll just have a quick look at, I've moved the camera, a quick look at this column. I'll put a bit of extra light on. There's our diffusion. Now, I've done this activity many times before. This visibly blue layer will take about a month to reach halfway up. If I'm careful and I don't bump it, just pure diffusion from here to there will take a month for that visibly blue layer to rise up. So that's what pure diffusion looks like. And it's really inefficient at big scale. We've got one of the comments from one of the teachers talking about oxygen diffusion in blood. When our blood gets out to our extremities, the arteries have become arterioles, have become small blood vessels, have become capillaries. And the same thing's happening there. When you go from a blood vessel, say 1 centimeter across, to a capillary that's 100 microns across, the surface area relative to the volume has now become enormous. And that facilitates that diffusion. So diffusion happens really quickly, but across very small distances. And that's why in living systems, where diffusion is happening, it'll be happening at a small scale. Where we need to move a lot of material quickly, we can't rely on diffusion. That's why we have a heart to push the blood around. So it's got to be mechanically moved. Diffusion just isn't fast enough. And so we'll come back to some of those topics. So we'll come back. Someone was asking about radiation in Ukraine. We'll come back and talk about that. So capillaries, very, very small, and that allows for diffusion across that. Because of our scale, we have to have a heart to pump the blood around. If you look at a simple organism, like a bacteria or a simple algae, or even some of the basic insects or roundworms, nematodes, one of the things that limits how big they can get is diffusion. Because they don't have, some insects have a circulatory system. It's not very efficient. But if you take a roundworm, then a big roundworm is kind of 1 millimeter thick and might be 10, 15 millimeters long. If you make it this big, it will suffocate. When it's tiny, oxygen can diffuse in, waste products and CO2 can diffuse out. It's all happy. Make it this big, make it the size of a snake, and diffusion is far too slow. So just think about that tank that we set up over there. We're seeing kind of how fast diffusion is, even across a few millimeters. So it's just such a powerful concept, this surface area volume ratio, because it turns up as part of the constraint that living systems have had to deal with. And so we'll see evolutionary adaptations that either take advantage of it or have come up with systems to work around it. But we can cover it because it's a really important topic in chemistry, as we saw. One of the other things which I like to share, really like to share, when we're working with students, young, old students, I'm sure you've done it. You've done flame tests. So you've put sodium salts into a flame and you've got a bright yellow color. You might have put copper salts in and got sort of blue green. And that's one of the pathways in, when we think about the color, that's one of the pathways in to kind of understanding or getting some evidence about electron shell structure. So later on in sort of chemistry, one of the things which students will struggle with is thinking about S shells and D shells and P shells and sp3 hybridals and all of these things. It's very abstract. It's very abstract, and so it's hard to remember. You can get there, and some kids have just memories that work that way. But for a lot of us, it's just hieroglyphics. It's very hard to understand. So flame spectroscopy is one of the things where we can help them understand that electrons are moving and that that's a certain amount of energy from one shell to another. And that gap between one electron orbit and another, that energy can correspond to a wavelength of light. And so from certain elements, we will get, when we excite them, heat, we excite their electrons, they will give off light of very specific wavelengths. And that's what we're seeing. Hopefully, a number of you have kind of tried and got the students to go and make simple handheld spectrometers. So just using a DVD or a CD while they still exist. In 5 or 10 years, it's probably very hard to find a CD. But because of the fine lines that are part of how a CD and a DVD are put together, we get that, we've got white light, we get these kind of rainbow colors coming off it. So these are diffraction gratings. And so there are a number of templates and how-tos out there on the web. Some very good templates by some of the Indian practitioners, Arvind Gupta and the team down in Pune have some very good templates that you can search for and find. So the idea with these is we use the CD as a diffraction grating. You can make this in a cardboard box. I've got a plastic tube. You put a very small horizontal slit in one end, so which is going to point towards the light. The light's going to travel down, hit the CD, be diffracted. The light will be split up into its colors, and we can view it through here. So hopefully, I'd be keen, if some of you have tried this, I'd be keen for you to let me know just in the chat box, or whether or not this is new to you. That's not going to look very exciting to you tonight. So what I've done is, here's a version. This is sort of the geometry that the team with Arvind Gupta, some of his guys have put together. So same idea. There's a CD in the bottom, slit here. The light comes in, diffracts off this and goes out through the eyepiece. But because we're doing this virtually, I've just put a little web camera looking in where your eye would be. All right, so you'll be able to see what the spectroscope is seeing. You don't need a web camera in your classroom. They've got their eye to have a look at it. So let's see what we can do. I'm just going to switch views now so that you're seeing what the spectroscope is seeing. The screen will have appeared to go black. I'm going to point the spectroscope towards the light in my room. All right, so we're seeing a range of colors. It's not a continuous spectrum, but it's fairly continuous. And that's I'll just check which lights I've got. Those are LEDs. Those are LED lights with extra phosphor elements in them to spread the wavelengths of light out. What I'm going to do in a moment is I've got a tiny neon globe. All right. If you've got some old equipment, some relatively old equipment, you'll sometimes have on the power button, when you push the power button down, sometimes on a power board, there's a power status light in the switch, and it comes on, it looks orange. Depends on the age of the equipment, but many of those power on lights are actually tiny neon globes, like the big neon signs. Now we call them neon globes because they've got neon in them. So that's the gas which is inside, and that's what gets excited, and that gives off the colors. So we're going to have a look at what the neon globe looks like in this spectroscope. And let me just get the globe out. This is just a tiny little one. I'll turn some of the room lights off, but it probably doesn't even need that. There we go. Let me just try and get that in the right spot. And you'll see, pretty sure what you're seeing there. So you'll see kind of two areas of yellow, orange, red. So one of those is the first order diffraction. The second area that you're looking at is the second order diffraction. So there's kind of two copies of that. And the shape of that slit, the shape of those lines you're seeing is the shape of the slit at the end. So if you're making these, try and make the slit quite narrow. So that will give you sharp lines and you'll be able to separate the different lines of the spectrum. All right, so I'll take the neon light away. Nothing. If I show it to the LEDs and the above, we've got lots of different colors. You can in fact point these spectroscopes, at the computer monitor and see the different colors that the computer monitor uses to make white or green or yellow or blue. And likewise, if you don't have a neon light, you probably will somewhere around the school. I would expect you'd be able to find it, but you'll certainly have red LEDs, green LEDs, sunlight. You'll have different types of light, fluorescent tubes. So the long fluorescent tubes use mercury vapor. And so if you point one of these at the fluorescent tubes, you'll get a whole bunch of different spectral lines to the ones which you saw before, which was the neon, which is kind of a strong yellow, a bunch of oranges, and then a couple of reds. So I like to share this. I'm glad some of the teachers have come back going, this is good. It absolutely is. They can make them, they can take them home, they can get to be a detective and go around the house and try and determine, work out what kind of compounds are in the lights that they're looking at. Which ones are incandescent, which ones are mercury vapor lamps, which ones are neons, all those sorts of things. They can come back and report back in. And it's just using cardboard, sticky tape, and an old CD. So I think very much kind of value for money, value for effort to put those in. So that's one of the activities which I particularly like. I think we've got time. There's so many things I would like to share. Let me leave you with something extra pretty. All right, something which is extra pretty, and a good thing to do with the students, and a good thing to talk with them about. And then we'll leave some time. We'll come back and we'll make sure that any questions about diffusion, you're happy with where we're at. All right. So for this kind of final kind of activity, let me get a bit of extra light in there. I'm going to put my jellies over there. And so just a plate, small plate is really what you're after. A little dished, so not absolutely flat. And to get the best result, you really want to have the table that it's on very flat, all right? My table slopes a little bit this way. And the other special ingredient here, you will need to see what you can find as kind of the Indian equivalent if you can't find these. These are M&Ms. Skittles work well, but we'll talk about how this works kind of in just a moment. I just need to make sure I've got enough water. Yes, there we go. All right, so the moment you bring these sorts of sweets out in the class, it's not only the teachers that get excited, but the students as well. And I guess we can all understand why. So what we want to do is, I always say that the brown ones are no good. We need to take them out. And that's true, but it also means the brown ones are there for the students or the teachers to eat at the end of the session. And so what we want to do is make sure we don't have any next to each other with the same colors. So we don't want any pairs of colors. We don't have to be too fussy about choosing an alternating color scheme. All right, that's got to be close to a circle. Nope. And I'm just going to pause for a moment and go and take the ammonia out of my room. It's working very well, the ammonia, but I don't need to be breathing it. All right. So there we are. They're all just touching. Make a circle as kind of tidy as you can. Try and make sure the plate is flat and level. And that's about as close as I can get my camera without it falling into the plate. All right, there we go, focus. All right, and now I'm just going to get some water, and to get kind of the best result, we're going to pour water in slowly but continuously until the water comes up to kind of halfway up the M&M, so kind of to the waist of the M&M, but I don't want to wash them all around, and I don't want to take too long doing it. So it's kind of a happy middle ground. So stop there, and then if you're doing this on a school table, the trick, the real challenge is to make sure that the students keep their elbows off the table so they don't bump the table. It really needs to be perfectly still. And perhaps you can see something happening now. Perhaps you can see it. What appears to be happening? What do we see? And some of you have fallen for my trap because we've been talking about diffusion all night. And again, this activity you may find online. It's a beautiful activity and it's full of science. But again, it's not diffusion. And we'll look at what it is in a moment. If we're using the word diffusion as kind of the everyday familiar English term, we would use the term diffusing because they're spilling out, spreading out. But from a scientific point of view, it's not diffusion as we mean it in science. So in fact, what's happening is the water is up. The water has come up to the middle of the M&M. The color in the M&M is contained in the shell. The inside is chocolate. And that shell is made from sugar. So we've got sugar in the dye as the shell. And so when the water comes up to the M&M, it starts dissolving the sugar and the dye is released with it. And so underneath each M&M, there's a little waterfall, if you like, of dense, sweet water, which has got dye in it. And so this sweet colored liquid, resulting because we're dissolving the shell off the M&Ms, is kind of sinking. It's only sinking a millimeter, but it sinks down, hits the bottom of the saucer, and then gets pushed along. And that's why, particularly in the early stages, we had these kind of tidy roadways, these pathways, kind of where the colors were bumping up against each other. They weren't spreading into each other very much. And that's because these are actually rivers of sweet colored water. And so they were flowing next to each other. Now that they've stopped flowing and they've been there for a while, now diffusion is starting to be noticeable. Diffusion's happening all the time, but it's very small scale, very slow. Now we're getting this kind of muddy color, this muddiness between those, and they're starting to mix. Because this is very shallow, there's probably not very much convection happening. So most of this now that you're seeing with this mixing from this point is probably diffusion. So it's always there. It's just whether it's the big driver in what we're seeing. So that's an activity that you might like to try yourselves. We're coming up close to kind of the end of the session, so the time we've set aside. I'd be really keen to get any of your questions, things which are still not sure on, not certain on, things which I haven't made clear. If you're not clear about it, that's my fault. But I don't want you to go away still a bit confused about any of the activities that we've done. So if you've got any questions about what we've covered tonight, now would be a great time to share them. So I'd love to hear from you. While you're thinking about that, look, thank you all for your presence today, and for the kind of the strong contribution that you've been making during the workshop, sharing your thoughts, because that makes it not only more enjoyable for me, but I get to find out what you know and how you're thinking about the activities that we're doing. So just to everyone here, I will put in the chat window now, as I said I would. So thank you for, I think it was Bieta reminded me that I was going to share my email address. It's not hard to remember. It's the Science Nomad. Science Nomad. So it's the Science Nomad at gmail.com. And certainly just feel free if you've got some more questions or you want some more details, just please shoot me an email. I will definitely get back to you as soon as I can. It would help me if you also kind of mentioned, because I won't remember all of your names, if you mention which workshop that we had together. So I've got a number of resources that I can share with you about the pH indicators and some of the other activities that we've done tonight. You're also more than welcome to, if you use Facebook, if that's part of your life, you can look for the Science Nomad on Facebook, and I have a page there where I will where I share some of the experiments and activities I do. And also if I'm doing other workshops in other parts of the world that are open to teachers, and I do a lot in India. So from time to time, there are other workshops happening in India that you might like to join. And if any of you use these activities, or you're doing a different activity in your teaching that you think I would like to see, so I can share it with others, I'm always open to learn from people who are actually teaching on that, because that's where the difference is made. So someone's asked for a website. I'm too busy to keep a website. I tried to keep a blog. I just could never keep it up to date. But the Science Nomad Facebook page is pretty busy. Several posts a week with activities or experiments that I'm doing, and you can pop a question there if you like as well. So you don't email or Facebook. I don't run WhatsApp groups or anything like that. Any final questions that you won't sleep if we don't answer them now? I don't want to be responsible for insomnia. Well, if there aren't any kind of immediate questions, I'll throw back to my dear friends at the Science Centre and thank them for the great work in helping to bring you all together and to be such good partners in this program for Science Week. And would certainly like to give a big thank you also to the Australian Consulate General there in Calcutta, which is, I've been working with the consulates across India, the Australian consulates, for some time, and they're great partners in education, as Australia is as well. So again, to all of you, thanks for your attention and your energy tonight, and perhaps some of you will come back for our computational thinking on the weekend. Suman, you're on mute.
I would request my colleagues, H.S. Satpathy, to propose vote of thanks, and he also gives some idea for tomorrow's sessions to the participants.
Yes,
Thank you, Stuart, for having a very, very nice and interactive and so exciting session.
No problem. We did have one question and a reminder that's come back. That's that I will answer quickly just now. People are understandably worried about radiation and some of the events which are happening in the Ukraine and what that might mean for younger citizens over there, younger children that are over there. That's the issues there are less about surface area and volume. The real worry is that young children are growing, obviously, hopefully, and because they're growing, they are laying down bone, and their cells are dividing very quickly, or more of their cells are dividing quickly. If they are exposed to the sorts of particulate radiation, so the radiation pollution, the radioactive pollution that's in the dust around Chernobyl, and that's being stirred up, which seems to be the case. A lot of the radioactive elements that are in that dust, if you take them into your body and you're developing bone, then a lot of those minerals can end up being incorporated into your bones. And because those radioactive elements have a fairly long half-life, that will mean you will get some long-term exposure from those. So it's not so much a surface area volume ratio, but more human biology. The young kids are growing quickly. They're pulling a lot of minerals out of their food to build their bodies. And if that food's got radioactive contaminants in it, that can lead to all sorts of problems. All right. Let's just hope the situation in Ukraine settles down very quickly. I fear it won't, but I hope it does. But again, thanks everyone. I'll throw to my friends at the Science Centre who will share what will be coming up in the next couple of days.
Thank you, sir. Thank you, sir. Thank you, Dr. Stewart, for your enriching session. And from feedback, we came to know that the session was very engaging and interesting to all of us. Now, dear all teachers, good evening to all. And tomorrow we are having another beautiful session at 11 a.m. And I, on behalf of my center, request all of you to attend this session at 11 a.m. and the session will be conducted by EIFR Mumbai. So we hope, Dr. Stewart, also, if you find time, you may also join with us.
I'd love to be a fly on the wall.
Yes, we do like that. And at
you.
the end, actually, we do have one session with Dr. Stewart, all teachers, for your attention. So if you have actually any query, if you think deeply after the program is over, and if we find any problem in doing something or generating the idea, we can share everything so that we can write up all our informations together and we can share with Dr. Stewart in the concluding day. So thank you all, and enjoy your time, and we hope tomorrow we meet again at 11 a.m.
Indeed. Stay safe.